Hi, we are the UMBC welders. We are Spencer Pear, Kevin Zimmerman, Kevin Wegner, and Arya Lax. So the product that we have developed for our Capstone is a spot welder for manufacturing sheet metal roofing in developing nations. Our customer, Dr. Zupan, is acting as an NGO who would buy the welder as part of an aid package. The requirements that we came out with, Dr. Zupan, is that the welder should operate with convenience of a DeWalt power tool. I want to draw your attention to specific system requirements. Of course, this welder has to weld, therefore it needs to have enough current. Also, it needs to be safe. Therefore, it should remain an open circuit without user
Now,
input.
to get us all
It
on the same
also will
page, we're
adhere
going to
to
start with
the
the
ENME
mechanical design.
standards.
These are a few of our iterations, with the most final one being on the right. The overall architecture is fairly straightforward and hasn't changed much. There's an arm on the top and a base on the bottom, and attached to both of these are triggers that need to be depressed at the same time for the welder to activate. The D prime trigger there on the top it's got a little bit more going on with the design than you might think. It has a pre-tensioned spring built in. This is to force the user to apply a certain amount of force. We found that welding pressure is extremely important for good quality in our research, so this not only ensures that the user only activates the welder deliberately, but is applying enough force to the probes while doing so. Speaking of the probes, because they are a disposable commodity piece that will be made as cheaply and as loosely toleranced as possible, we needed a mounting solution that could accommodate this. So we went with a simple V groove with a thick bolt through the middle in order to make sure we could accommodate bolts made to fairly loose prototypes, which we'll talk tolerances, which we'll talk about in a second. Now in the base, there's a fair amount going on. Almost everything in the welder is in the base. So I wanted to touch on that. You'll see the capacitor bank there on the left, the rechargeable and removable batteries there about in the middle, the Arduino Nano controller towards the front, and I also want to call your attention back to the left, where we've got the hinge pass-through. We ended up realizing that we needed four 12-gauge copper wires to pass an appropriate amount of current to the probes, including the one on the arm, so we needed a pretty large pass-through cavity through the hinge for those wires to travel through. Alright, now here are some of the drawings we generated as part of manufacturing our design. There's one of our probes. We encountered some unexpected difficulty making the copper probes to tolerance, but because our design mounting solution was robust, we can still use this probe perfectly fine, and we're very proud of it. There on the bottom, we've got our acrylic plate cutouts. We first tried to manufacture these by hand, encountered some issues, and today we are having these laser cut.
So we used initial simulation to select the conductor size, and the tests consist of a full cycle of battery charging, priming the capacitors, and depriming the capacitors through the steel to create a weld. On the left, you can see one test where we measured the temperature as a function of time at 4 millimeters from the weld spot, and on the right, you can see a separate test where we developed a carbonized spot indicating that the temperature rose above 400 degrees Celsius. We used this test data to refine the simulation using these scaling assumptions, if you're interested. And we used it to refine this thermoelectric simulation where the heat dissipation and the heat capacity are combined with the amperage and the resistance to generate temperature as a function of time. We manually tuned the first combination of heat capacity and heat dissipation to reflect the test results. And then we used the scaling assumptions shown earlier to find an optimal plate thickness.
So for our coding design, it cycles through a switch case structure. There are three main modes. The first being the priming mode, which charges the capacitors and then switches to the waiting mode. In the waiting mode, it checks to see if the capacitors are still charged and also if the triggers are pressed. If the triggers are pressed, then it switches to the priming mode. In the third mode, the priming mode, when the triggers are pressed, the capacitor discharges for the pulse time length. Also, there are two error modes, one being if the battery is too low, and two being if the system is too hot.
So to make this all happen, we need a pretty sophisticated set of both high power and control circuits. This is our high current board, which holds our capacitor bank. It has to be able to prime the capacitors up to the 2.5 volts that they need to be charged to, and discharge them successfully on command. And to do that, we have a set of 4 very high current MOSFETs that will tolerate our up to 800 peak amp current load. Next slide, please. We implemented a off-the-shelf CCCV power supply. This was to replace our own design, which would have cost us too much money and would have decreased the reliability of our product. So we used this off-the-shelf component to simplify our design and reduce the costs. Next slide. We developed a control board to deal with all of the various inputs and outputs and to monitor the safety of the system, both the temperature and the battery voltages. Next slide, please. And we have a user interface board, which is mounted actually in the top plate, which communicates information to the user via sets of
Now,
LEDs,
fabrication has been a
through
bit of a
blink
story. A
cycles
lot of
and
our parts were 3D
on and off
printed,
states.
which became a complication when both of our 3D printers died. Rest in peace, Monoprice Select Mini ANET A8. Hand-cut acrylic, as we mentioned, presented some complications, but we have overcome those and are also getting the parts laser cut anyway. The high current PCB, for safety and reliability and just the complexity involved, was manufactured at the JLC PCB fab house, but the control electronics were manufactured on proto board because it was more lean. This turned out to be a great decision because we had to implement battery level monitoring and after we had made those boards. And we used an Arduino Nano for the microprocessor and many screws for fasteners. Here's our timeline that we followed getting up to this point. I marked out in the beginning of November where we started to slip behind some of the team set deadlines. However, we had enough margin in our timeline that we have still met the assignment deadlines, and we are still well on track to be finishing and demonstrating our prototype on time. We also have December 16th looming over our heads when all of our reports, presentations, portfolios, and such are due as well. These are our references, and we'll now take questions.
Nice job, and Dr. Zupan, it looks like he's clapping for you as well.
Thank you.
And so Noelle, we'll start with you. Any questions?
No questions. Great work, guys.
Yeah, really, really, really well done. And Dr. said him not being very helpful. Dr. Zupan, you're welcome to unmute yourself as well, please, and to say whatever you like. So I'm curious, did you actually, I didn't gauge this and maybe I missed it, were you able to actually form a weld?
We have not been able to
Kind of, yeah.
obtain plates thin enough that the simulation indicates we will be capable of welding it. However, as you saw in one of the earlier slides,
I'm going to jump in here just to piggyback on Zupan's comment.
Yeah,
he did give us the advice to go to a local metal house and get thinner metal. I just haven't gotten around to doing that because after seeing that spot, I'm like, all right, we're on the right track. We got to get this thing built, and then we'll get the equipment to test it. So that's coming up before we demo.
I'll be blunt. If this was not a COVID time, they would have a welded joint. But the ease of just being able to pick up the right metal to weld goes from being you pick it up on your way home from school to it's actually a real problem right now.
Yep.
Especially the nonsense of COVID. So if this was a different semester, they would have a welded joint. I'm certain of it.
We also that weld test that produced the spot was not from a full 2.5 volts. It was only from about 1.4.
Actually,
it was only from about 1.4 volts to 1 volt. So if we went from the full 2.5 down to 1 or 2.5 down to 0,
I was wondering if you're using your entire amount of power.
We are not, and that's to expedite the tests because with the new charging circuit, we charge the capacitors quickly, but we want to do them quickly. So
Okay.
we are going to plan to do a extended 2.5, a full test. So we'll probably get even.
Well done, guys, and
Thank you.
congratulations,
Thank you.
by the way, on your very last
Yes.